Hey there. Welcome to another Toolbox Tech Talk. Yeah, you're back here at the Smart Energy Lab with me, the guy with a lot of bling. Yeah, anyway, we can take my glasses off. Just first up, welcome everyone to another Toolbox Tech Talk. And look, my heart goes out to all of those in lockdown in New South Wales. I mean, it's a really hard lockdown for parts of New South Wales now. So yeah, only essential workers can leave their area. Melbourne's kind of got used to it. We've done number 5. We've had a lot of hard ones, but it's always hard, especially if you're a small business and you basically have to stop working. So, yeah, I feel for you all. And I thought I'd just put this on as a bit of a lockdown special, you know, something to entertain you when you're not watching the footy or looking out the window wondering when it's all going to end. Yeah, so today the focus really is, and this is thanks to all those on the Solar Cutters and Quality Solar Group who gave me some feedback. This is all about off-grid system design and batteries. Well, they kind of go hand in hand. If you're off-grid, you'd be mad not to have batteries. I don't know what you're going to do, candle power. But yeah, so it's kind of like looking at both of those. And really, it's a subject extremely close to my heart because I've lived off-grid nearly 30 years now. Actually, I have 30 years. I've been living off grid. I had a little stint back on grid for a couple of years in Canberra. That was interesting, having to pay power bills for a little bit. Whoa, that really gets you. Yeah, so I've got a lot of personal experience in this area. I live in an off-grid community, Murramurra Co-op in the mountains just to the east of Melbourne. So in the Mount Toolbox, which is a really beautiful place. I think actually I might even have a picture of it somewhere. Let's have a look, see if I can grab it for you. Yeah, so Mount Toolbox, we're about 700 meters up here, and yeah, so it's a cool place. So there, I'll just pop it behind me. Yeah, I'm doing a green screen, so I'm not really in my studio because it's too cold out there at the moment. It's like 5 degrees and it's unheated. So I'm afraid I'm a bit of a wuss, and I'm in my office with a green screen. But anyway, look, if I turn my silly face off, you'll be able to see a bit more of that beautiful background. There we go. So that's Mount Toolbox. There's 70 people live on this housing co-op, been off-grid since 1974. There's 30 homes, and there's a whole mixture of standalone power systems. Now, when I say standalone, some of them are individual systems. That means they've got their own solar and batteries and maybe a backup generator or maybe a shared backup generator between a few homes. Others have a centralized system where they have no solar or batteries at their home, but they have a central solar system that provides basically AC power to 5 homes. And then there's the one you're looking at right now, which is my cluster of 7 homes, a microgrid where we share energy between the houses. So we've got a central microgrid system that effectively forms a stable grid to which all the homes can parallel their own systems to, just like they would if they're sitting on the utility grid. So there's a kind of a whole range of different options. So I'll just bring myself back into the world. Where are we? Keep back on. And I think I'll just pop back in the studio because it's nice and cozy in there. So there we go. Yeah. So I also do, for those not familiar with what happens here at the Smart Energy Lab, I do a lot of testing of systems, field testing. So it's not like a test lab. You get a certificate. Basically, product comes here. I review it. I get my electrician and I install it together. We kind of give feedback on the product. We sometimes produce reviews about the product online. So my YouTube channel, Smart Energy Lab, you'll find lots of products that I've been looking at here at the lab. We use a lot of them, and I call them part of my permanent collection, those systems that actually are really useful on an ongoing basis, not just sort of some new widget that I want to show you. So, a lot of the systems here are fully functional. Now, I want to let you know that you're welcome to come and ask questions today. So just in the chat, you can type some questions. But also, if you're feeling brave, I'm going to put a link in the stream. So you probably see a little link pop up there. You can actually click on that and you go into what's called the green room, which is a little room where you're not live straight away, but I can see that you're sitting in the green room. If you turn your microphone and video on, and I can always bring you on for live questions. So if you did want to, just pop up on screen with me and have a chat about something, we can certainly do that. So there you go. Feel free to participate live if you're feeling brave. So the program, I'm going to start off with a bit of a walk and talk tour of some off-grid systems here at Murumura Co-op, and just kind of talk a bit about the experience of living off-grid. Then we'll move into things like what are the key considerations when designing an off-grid system, and things like what type of batteries to use, where should they go, what's the right size PV system, and I also have a simple formula. I've shown it many times on my channel, but I keep popping it up there because it's actually not rocket science to size an off-grid system. It's not even rocket science to size an on-grid system, but there you go. So we'll look at that. Now, what I did, it's actually kind of interesting. We're having a bit of a crisis here at the Smart Energy Lab at the moment. Our main backup generator, which is a about 8-year-old 22 kVA three-phase generator, broke down the other day. And on the worst possible time of the year, basically a week of rain ahead, batteries are all virtually empty. We had no backup. And that's really a lesson for living off grid. If you have only one source of energy, maybe that's, solar and battery, and something goes wrong, like the weather, then another source of, a reliable power that you can call upon really can save the day. Now, I sometimes say it's a personal choice. Really, you could say black is the new black, i.e. blackout is the new black. You lose power, you wait for the sun to come back. Now, that's not really a very enjoyable way to live. Certainly, if you've got food in the fridge that's going to go off, that you've got kids that you're trying to homeschool, like we are here in Victoria at the moment, and probably New South Wales. You don't want to be just sitting in the dark for a few days waiting for the sun to come back. So having a reliable backup generator is pretty important. And ours failed, and we've got a wonderful diesel mechanic here who straight away came around within hours, checked it out, and said, "Oh, Glenn, your automatic voltage regulator's failed. You'll have to order a new one." Now, those things don't just sit on a shelf, and I should actually have a spare. Second time it's failed, by the way. So, I better order a spare. So we had to go and order one, and so we're sitting here trying to repatch the system together to keep it running with a little tiny 2 kilowatt generator. So that's kind of the experience of living off grid is managing power. A really well designed system will kind of more or less look after itself, but there's always some maintenance to consider. Yeah, so I think first questions come in here. I'm going to throw this up on screen. Thanks for that, Heath. And just a comment from Heath. There we go, bring it up. So Heath says, black starting an AC coupled system is not fun without a generating set. So there's a first technical term that I want to explore. What's a black start? A black start, well, I should start with AC coupling. If you have an AC coupled system, that means that you have a battery inverter and a solar inverter. You've got two inverter systems that work together. And the way the power is shared between them or transmitted from the solar inverter to the battery inverter is through your AC network, through your switchboard. Now, the problem with AC coupling is it's possible if the battery inverter shuts down, and that often will happen at nighttime, winter when the power, demand is high and the solar resource is low. That battery inverter effectively is a grid forming system. So if it shuts down, even in the morning when the sun comes up, your solar inverter won't have anything to synchronize with and therefore won't turn on. And so I had exactly that problem this morning. I went out there. It's a bit foggy, so there's a bit of solar coming in, not much, but the battery inverter system, it's a 30 kilowatt power chain from Selectronic. I'll show you that in a minute. It had shut down. So I've got light, but I got no charge, and I had to do an emergency restart of the system to get it working. Now, there are solutions to that, and I'll talk about that in a bit with a walk and talk show. I'm going to take you around the place in a minute. So yeah, thanks for that one, Heath. That's definitely true. If you don't have a generating set which can form a grid, which can cause which can recharge the batteries, which can bring the solar inverters back on, you may have a bit of a challenge. Yeah, so first up, let's bring up here. Now, what I did, I actually just walked around with my iPhone this morning in the fog. Well, I think it cleared a little bit here, light rain, and filmed some stuff. Now, this is where I live. My house is on the left. My neighbour's on the right. There's actually 7 homes in a small circle here. There's 30 altogether on the property, and we have a lot of shared resources. In this cluster, we share energy. So we've got a microgrid. So I'm just going to press play on this and pause it from time to time. So first up, good orientation really matters. Now, people often say, what's the correct orientation for a solar PV system for off-grid? Well, it sort of depends on when you need the energy, but predominantly a north-facing array, or more correctly, an equator-facing array, because if you're in the northern hemisphere, of course, it would be the reverse. An equator-facing array will give you the best production. Now, for customers on grid, that's not always the same story, because you may be exporting energy if you're not at home, and so you're losing it. But if you're off grid and you've got batteries, you're likely to be able to store it for nighttime use. So having a good northern aspect really is a bonus, but don't rule out any other arrangements. Really, it's all about how much PV will achieve the job that you need it to do, and you can calculate that for any orientation, any inclination. So, this is just looking at my neighbour's house here. She's got actually 17 kilowatts of solar on the roof. You can't see it all. It's on both sides. She's got south-facing arrays, north-facing arrays, steeply inclined north-facing arrays. We really maxed out her roof for maximum production. And that's a bit of a lesson for off-grid these days, really having an oversized PV system. I mean, she's an energy miser. She lives on about 5 kilowatt hours a day. 5 kilowatt hours a day, and she's got 17 kilowatts of solar on the roof. Well, what's she going to do with it all? Well, on a day like today, when it's raining, she's actually producing as much as she needs. So that's a plus. Oversizing means that even on poor days, you're not drawing on your batteries. So oversizing has some real pluses for system sizing. Now, I'm just going to jump forward a little bit here and around a little bit here. I must have been in slow-mo mode. There we go. Just turn the camera around a bit more. And there you go. So she's actually building an extension of my house, and her stepdad's there with his building tools. So that's what you're looking at there. That's the my house on the left. And as you can see, I've got a lot of solar on my house as well, about 10 kilowatts all up. A lot of it actually is partly to benefit the shading potential of solar. If you look carefully, and I've got a closer up video of this on the sort of your right hand side of my house, there is a very steeply inclined pergola which shades the western side of the house, and it's got solar panels on it. Now, really, the main purpose of that steeply inclined array is shade. It's to shade the house. It's not really much about generation, but solar panels are actually a very cheap shading device. In fact, I sometimes joke that they're the only government-funded building material out there. So that's pretty nice. Oh, there we go. My regular, hi Bradley, great to see you there. I'm just going to bring his comment on. So Bradley says, thoughts on splitting 1/3 east, 1/3 north, 1/3 west. So Bradley, if you have got a sufficiently well-sized storage system, I would actually go all north. If you can, because it will give you the maximum production over the day. And, if you really wanted to squeeze the most out of it, you'd probably want to have an optimum orientation for the worst load resource ratio. Now, that's a new term. Load resource ratio is what time of the year is the ratio between your energy use and the amount of potential energy coming in from renewable sources like the sun. And that ratio is generally worst in southern states of Australia and New Zealand in wintertime. So for a residential installation. So that means actually quite a steep incline will give you the best production during that time of the year when it's most difficult to meet the load requirement. Now, in terms of splitting the arrays between multiple orientations, nothing wrong with that at all. I often say the roof demands where you put the panels. If you have a roof that faces east-west, stick with it. More panels can cover off any loss efficiency due to orientation, and therefore it's often cheaper just to max out an east and west roof arrangement than try and tilt them to the north. So tilting really is a bit of a bygone thing. In fact, you're looking at a picture there with some tilted arrays on them. Really, I probably wouldn't do that again, but they were installed over 10 years ago, so I probably would have just followed the roof profile. And Bradley asks something like, is the ladder shading the panels? No, it's not actually. I spend so much time going up and down onto my roof that I've got a permanently fitted ladder between the first story and the second story, and I can climb out a window, which is kind of convenient without having to, put a ladder up the side of the house. So there you go. A lot of fiddling around. And we've also got a comment here from TRME the Weasel. Not sure how you say that. I use a small solar tracker with 3 200-watt panels. Good little setup. Now, I'm glad you mentioned that, because solar tracking, I've had a kind of love relationship with solar tracking. Early days of solar, like over 30 years ago, tracking was really a great way to squeeze the most out of your system. And in those days, my first panels cost $750 for a 75-watt panel. So that's $10 a watt. I can still remember buying them. And so you really wanted those panels to work as best as possible. And often systems were very small. I literally had 3 panels, just like Mr. Weasel says. And we would have a seasonal tracking system where we adjusted their tilt angle, or even better would be following the sun from morning till afternoon. But then panels got cheap. And so suddenly trackers had a negative, which was this extra cost to get that extra performance. And that difference was about the same as buying more panels. So really the benefit of tracking sort of went away for a while, and you've also added mechanical failure to the mix. So, will your tracking system reliably work? So that was a bit of a consideration. But then tracking came back again, particularly for large-scale solar. What you're doing is getting more production per hectare, off your solar farm, and you're also getting a much flatter generation profile. So single-axis tracking now is 70% of all new build solar farms in Australia use single-axis tracking. I've got a couple of 30 kilowatt trackers here, the single axis trackers out in the paddock, demonstration units. And what I noticed is that particularly in summertime, they just turn on at full power, at sort of 8 o'clock in the morning, full power, 30 kilowatts, pretty much flat the whole day, 30 kilowatts till sunset. So you end up with like a generator, basically. It just turns on because they're following the sun perpendicular the whole day long. And that's a great generation profile. No peaky bit in the middle of the day. Early production when your batteries are low in the morning is a great thing. In fact, that's probably a pickup from what Bradley asked before. There is some merit in having some east-facing panels because they do help you recover from a bad night of self-use. So that's another one to consider. And Mr. Weasel mentions that he made the tracker back in 2011 because that's right, panels were expensive. And he also says, yes, failed last month, but I fixed it again with $12 new LEDs working. And great to hear. I mean, I really, tracking, especially small tracking systems like Mr. Weasel's talking about, really are great hobby projects because, if you're into electronics, it's really fun to, make stuff move. But probably for many people, the simplicity of just fixed arrays is probably the right choice. I don't want to diss what you've just said, Mr. Weasel, but for many people, they don't want to have to fix stuff. So they just want it to work. So there's pros and cons of both approaches, and you definitely, without a doubt, will get more production from a tracking array, all things being equal. Oh, g'day, Edwin. Edwin says hi, and would you say that there's a point in diminishing returns in terms of overloading your PV with your microgrid, overloading your PV? So oversizing, I guess, is what you're referring to there, and diminishing returns. Well, it all depends what those returns are and what the cost factors are. There is ratio limits when it comes to how much overpowering you can put onto a system. Now, there's a couple of limits. One would be the maximum charge current that you can put into a battery system. So, you need to be able to limit that to suit the battery manufacturer's requirements. But also, if you have an AC coupled system, the ratio of solar inverter power to battery inverter power has to be considered. Now, many manufacturers will give you a number, typically 1-to-1. Some will let you go beyond 1-to-1, but that does kind of become a bit of a hard limit. So here, just to give some numbers, Edwin, we've got about 100 kilowatts of solar, and we've got a 30 kilowatt microgrid. So you could say we're more than 3 times overpowered. But because most of that is a comms controlled solar farm, so that means it's controlled directly by the battery inverter with a data cable. It can reduce its generation in milliseconds, so it can manage that huge amount of overpower potential. Wow, questions coming in left and right. Before I go back to, sorry for calling you Mr. Weasel, but the TRM, though, Weasel's a bit hard to say. I'll come back to your comment in a minute, or question about the batteries. And in fact, I think I'll even answer it with a picture. So I'm just going to take this little view off screen here and bring another one on. So I've got a few, I call them walkabout tours. I've got a few little walkabout tours that I did this morning. I'm going to backtrack a little bit and show you a small system. So it's not all about big. Sometimes small is beautiful too. Yes, indeed it is. And this is a tiny house. So let me just bring that up on screen for you. So here we go. Click the right buttons and you'll see it. There you go. So this is a tiny house. If you haven't heard of the phenomena, basically something on wheels that, in many jurisdictions isn't deemed to be a permanent residence. So, you can bring them onto a property and you can live in them, but they start to look very much like a house, but small. So this is a tiny house, 1 room, 2 lofts, master bedroom in inverted commas above the front door that you can sit up in, and guest bedroom in inverted commas above the bathroom at the far end of the little tiny house. So you can pack a lot in there. Also, it's got tiny energy consumption because it's designed with energy efficiency in mind. LED lighting, efficient fridge. It's got gas cooking, so you could say, well, that's a bit of a negative from a renewable point of view. But she is moving to all electric, so she is going to put an induction cooker in, but she's going to have to add a bit more PV. So she's got 4 panels, 4 200-watt panels. 2 of them are actually PVT. That means photovoltaic and thermal. They heat water, the big fat thick ones on the left-hand side. They heat water as well as generate electricity, and the other 2 are just plain photovoltaic panels. So she's only got 800 watts of panels, which seems like a pitiful amount, but actually it's enough for her, being such an energy efficient home. So let me just kind of press the play button there. It is actually raining. my phone was trying to focus on the raindrops, I think. It keeps kind of flicking around there. All right, so she's talking to me. I'm just going to jump forward a little bit in this picture there. She's just waving, wondering why I'm filming it. No, she's saying hi. And the other thing I wanted to show is water. Now, I'm going to cover a bit of territory here. When it comes to off-grid, it's worth considering all the energy sources available to you when you design a system. When I say energy sources, electrical, wood, gas, water, wind. There are many sources of energy, and you need to kind of do an assessment of those and what ones are the best match to your needs. Now, what you're looking at here, sorry, it's a very slow pan, is a water tank. Yahoo! This water tank is storing water that comes off about 5 roofs in this cluster, and the water is at the lowest point. It's below all the houses. Now, normally that's a problem because you've got to pump the water, at pressure to deliver it back to a home. So you want pressurized water, and that uses electricity and it uses energy whenever you turn the tap on. But what we've done on the other side of that tank is a Lorentz solar pump. And it's actually connected by fixed voltage wiring. It's got a 48 volt fixed voltage input as well. And it's using surplus solar energy to pump water up the hill. Now, I'm going to flick you up the hill really quickly there. So about 20 meters above, in vertical head, above that tank, behind the trees in the distance, too far for me to walk, about 200 meters away, is a 260,000 litre tank. One of those big, assembled on ground corrugated iron with a liner tank. And so the water's pumped up there using effectively surplus solar energy. One of the things about an off-grid system is it's use it or lose it. If your batteries are full and it's still sunny, you've got to use that energy, or it's not going to be converted and producing anything useful. So it's pumping water up the hill. Why is that useful? Because it's now stored energy. It's 20 meters vertical head, which is about 2 bar, or exactly 2 bar, and that's reasonable pressure. So you've now got pressurized water coming back down another pipe parallel to it, supplying all the homes. Why I mention this is that means that you've taken out of the sort of daily energy budget a pressure pump, because you're using surplus solar, which is free energy. You're storing surplus energy as water at height, and then you're providing also resilience in a system design. That means if your inverter fails, your electrical system goes down, you've still got water. You can flush your toilet, you can turn your taps on and drink it. If you've got a firefighting scenario, you've got water. The pressure might not be great, but depending on the head. So you've got water, which is a vital ingredient of life. So there you go. That's something to consider. I'm just going to look through some of the questions that are coming in here. Don't get me started with wind. Yeah, that's probably my comment too, Mr. Weasel. So I'll come back to that one as well. Now we've got wow, you guys are going for it here. I'm going to have to scroll back on my feed to see them all. So we've got Craig. I'll just bring Craig's comment up here. So Craig says, I'll just take the picture of the car off the screen. There we go. Craig says, just pick up a further 12 270 watt panels, and we'll put these facing west so you can run the AC to late into the evening. And using a Victron MPPT, what's the best string fusing option? Okay, well, Craig, a few things to consider then. So you're talking about using a maximum PowerPoint tracking charge controller, and the Victron, excellent product, has a maximum input voltage of 150 volts. So you'd have to make sure that under the coldest operating conditions, the strings were short enough not to exceed 150 volts. So I'm guessing with those 270 watt panels, probably strings of 3 would be okay. Most of your 60 cell modules will top out about 40 volts. So 3 of that's 120 volts. So strings of 3, that means you've got 4 strings. Now, this is where it gets a bit complicated, and I probably would need to, actually, I've got a drawing. Hold on a sec. No, I don't. Hang on. I do have a drawing. Wait a minute. I knew there's a reason for me setting up my drawing table here. Craig, really simple explanation of string over current protection is that when you have multiple strings of panels, and so a string is a series connection of panels, there's one string. When you've got multiples in parallel, a fault condition, one string can backfeed another. And so there's a requirement to that ... meanings more panels. It's a requirement to calculate the maximum reverse current that any one string can take. Now, that's often known as the series fuse rating. Series fuse rating, okay? So the series fuse rating. Many panels have these days about a 15 amp series fuse rating. Some go as high as 35. Let's say it's 15 amps. So that's the maximum current you can pass through a module in either direction, forward or backwards. And under fault conditions, you can get reverse current. So if we put your Victron MPPT over here, symbol for DC-DC converter, so that's our Victron 150 / what was it, 85 amp MPPT. And what we're doing here is connecting up, and I'm going to draw those extra 2 strings really quickly here. By the way, this applies to on-grid systems as well. I'm drawing an MPPT here, but it actually might have been a inverter. And the requirements I'm drawing come straight out of a standard called AS NZS 5033, which, by the way, is just being updated at the moment. So what I'm telling you now might change by the end of the year. But I'll just take your question off the screen so we can see all of my drawing. So Craig, the issue you have is if you parallel those 4 strings and you have a fault in any one of them, so let's parallel them all up together. And because it's probably a floating array, that means it doesn't have any reference to Earth, you actually need a couple of faults. So let's put in a wire gets damaged on the roof and touches the conductive parts of the frame. And somewhere else in this system, you have a similar fault. And you now have a fault path that allows current to flow through, in this case, in this direction, through like this. So we've got 3 strings flowing in reverse into one string, and the loop path will be back through here. There you go. So that fault condition would mean that the short circuit current of 1, 2, 3 strings is flowing in reverse. Now, if it exceeds that number, you need fusing on all strings on both poles. So it's all about knowing what the short circuit current of the module is. So let's write that in here. So we'll go, the short circuit current is 9.5 amps. And so 9.5 plus 9.5 is 19 amps. Straight away, we've exceeded that, so you'd need string fusing. So basically, once you went beyond 2 parallel strings in this configuration, string fusing would kick in. But it all depends on that number there. You may find panels with a higher fuse rating. By the way, what you do, you put them at as close as practicable to the point of combining of the strings, so basically the ends of the strings, and you have to have string over current protection. They can be fuses or circuit breakers, appropriately designed ones, for both the positive and negative pole of the strings. So there you go. Thanks for that question, Craig. That was a great one. So I'll just cut back. There we go. And where have I gone? Disappeared off the screen. Okay, let's bring myself back on. Here we go. How was that, Craig? Did that kind of answer your question? Nod if it was. Oh, we've got a guest in the green room now. Louis, I can see you're in the green room. Just to mix things up a bit, did you want to come on? If you do, yeah, you got your camera there. Have you got a microphone? Yeah, you look pretty set up. I think you know what you're doing. Give me the thumbs up if you'd like to come on and have a chat. Okay, here we go.
Yeah, good to meet you, Glenn. Yeah, I can hear you now. Yeah, we're getting used to all these Zoom meetings at the moment. That's all we do now in lockdown, don't we? So it's just one of those things. But yeah, both Glenn and I are both on the EL 005 committee. I'm fairly new to that, so I'm just getting my head around that process. You're a bit more experienced, Glenn, in that field, I believe. So.
Yeah, about 10 years I've been on the committee, yep.
Yeah, so yeah, I'm just getting my head around that. So as I get used to it, I'll probably put more input, and I'm trying to also get on the EL 0042 committee. So that's the next one. That's the one that I'm very much interested in. So
you've missed the good days of the gravy train. We used to get a sandwich and a cup of tea at committee meetings, so they were the good days, but now it's all Zoom. BYO.
Yeah, I know. We can't get those nice bickies and coffee through our computer, can we? So we have to make our own. So one day we'll get together again, won't we? So yeah, looking forward to that day. But yeah, no. My role is I'm actually a technical manager at NECA, so I actually help. I'm actually an electrical inspector myself, so I actually help guys answering all those compliance issues. So, and I also go around the state doing some special talks where guys can get points to their CEC accreditation. So I was meant to go up to Swan Hill this Tuesday, but that's all been thrown out. So on Friday, all I was doing was cancelling everything, all accommodation, meetings, and you know how it goes, Glenn.
Yep. We all want Louis the super spreader. That's right.
Yeah, that's right. So, so I've been told to stay back in my Melbourne home.
So, Louis, a question for you. You mentioned that you get a lot of compliance questions through your role at Nika, and as an electrical inspector, that's kind of your job, is to know the standards.
That's right.
Is that an easy process to answer those questions?
Look, there's a lot as you go into it, and also myself, I'm CC accredited in solar grid design as well. So I used to actually install systems in the Yarra Valley where you are, Glenn, so a few places. But yeah, around that area of answering compliance, as we all know, there's not just one book to look at, there's a lot of books to look at. So, and some of them sort of contradict a little bit one another, so you sort of go with the one that's more connected to the job they're doing. So there's a few things in 4777 that overrule the requirements of AS3000, so because they're more specific to what you're doing. So that's the fun part of the inspecting side. So which you would understand, like in 5139. One little thing that bugs me over many years is the adjacent rule. We seem to have different distances all over the place, don't we? So it's either 2 meters, 3 meters, or 1.25.
I know, yeah, it is. It would be nice if we came up with a common definition of adjacent. But I often say that you've got to look at what the underlying principles were. What was the intent? And many of those adjacent is all about safety. So it's, can you see the point of isolation? Can you reach it if you need to? Those are the kind of like the key considerations. So I guess sometimes common sense applies. If you've got a main switchboard inside the house and on the other side of the door is an inverter, you might be within 2 meters of it, but only if the door's open can you actually access it. So you got to think about, the application of that.
That's right. We quite often, as an inspector, people would have their switchboard on one face, and then they got the inverter just around the corner, and guys didn't put the AC isolator next door to the inverter. So then I would have to say, no, that doesn't comply, because when I'm standing in front of the switchboard, I can't see that inverter. So you have to be able to see it. It's in line of sight, not necessarily always the distance. So that was a common one. If it was only with, it could have been just 1 meter away around the corner, but it's not good enough. If you can't see it, the other one where you're standing, basically it doesn't comply.
Yeah, cool. Hey, Louis, I've got heaps of questions coming in on the chat. I might have to go back to them.
That's all right. No worries. I'll stay here. And
Yeah,
no worries.
Okay, I'll pop you back in the green. All right, thanks, Louis. This is a very interactive audience, so thank you very much. And I'm just going to start working through some of the questions that come in. And yes, James. Yes, okay. So James asks, can the solar pump also be configured to run when the generator is running? So I think you're referring to that picture that I just had up on the screen before. I'll just bring it back up here, where there is a tank up the hill, a sump tank as it's called, at a low point, and the pump is using surplus solar to pump it up the hill. Now, that is just a design scheduling arrangement. Do you choose to use an indication there's surplus solar? That could be battery voltage, state of charge, a float condition from the charge controller to trigger a pump? Or do you use some other information, such as when the generator is running, there's AC output on the generator circuit, and do you use that to power the pump? So that'll be a very easy one to do, James. So if you've got a generator only outlet, as well as that's not fed by the inverter, so it's on the input side to a bidirectional inverter, that generator outlet will only turn on when the generator is running, and if it's got a pump connected to it, that will just pump water. Bingo. You probably need to consider overflow as well, so having a float switch on the tank is a good idea, so that you don't just pump the water onto the ground and cause erosion. But yeah, that's a really easy one to do. I like the solar one because you're using free energy, but whatever works for you. James also asks, let's have a look here. In a scenario with unavoidable shading at certain times of the day and year, are DC optimizers such as the Tigo still useful with modern quality solar panels, bypass diodes, and modern quality maximum power point trackers? Wow, you can get into some hot water when you start talking about string inverters versus optimizers versus microinverters. In fact, my friend Mark Kavanagh has done a recent video on this on his channel. So MC Electrical, Mark Kavanagh, if you search for him on YouTube, you'll find he's done a very empirical test between a string inverter, a micro inverters on the same roof, same panels with different shading arrangements and looking at the effects. And there's no clear-cut winner. It depends on the nature of the shading. So, yeah, I guess when it comes to shade, it's definitely going to have an impact, whether you choose to optimize or not using things like DC-DC optimizers like the Tigo or a microinverter system. It's all down to cost and performance. They both work. I mean, you could actually just have a bigger string system. Losing some panels in a string isn't the end of the world because they do have bypass diodes. So there's no automatic answer to that one. But I should point out that the fans of optimizers also love the data they give you. So you start to see every single panel's performance and whether there's a fault. So that can be a big plus as well. And with some designs, you can run very long strings because they manage the voltage. So you can have long strings of panels without exceeding regulatory voltage limits. Thanks very much, James. Gee, I'm not doing very well at getting through my slides. Before I answer the next question, I'm going to take this picture off the screen here and bring up another little walkabout tour. Let's have a go here. Right, so I was talking about, I'm going to bring it on the screen so you can see it. Share screen. Sorry, it takes me a moment to do this. There we go. Right, so this is a side view of the western side of my house. It's a straw bale house, by the way. Straw bale being an excellent material for a cold climate like we are here at Mount Tillybong. The panels that you can see there, I think my mouse might even point to them up there. There you go. These panels are just really waste panels. They're old Canicas. They were removed from a customer's roof because they wanted more production off their roof. Those panels are only 60 watts each. So they're 1 meter square, but there's nothing wrong with them. They still work. And also, as my friend Jerry, Jerry from the Greenhouse Effect, who used to work for me but now has his own business, the Greenhouse Effect, he said, Glenn, rather than us putting up all this wood on the side of your house as a pergola, why don't we just use some of those old solar panels you got out the back? And so we actually, just put some solar panels up and they still worked, so we connected them up. So there you go, there's 600 watts of solar pergola shading the western side of the house. Now, if I press play, I think I'm going to just walking past the fire hose and have a little survey around the side. Now, some of the considerations too with location of solar panels, there's rules about how close you can go to an edge, and that's basically complying with mounting systems that come with an engineering certificate. But it is possible to engineer almost anything. Like a solar carport has no edge limits because the whole roof is solar panels, but it's engineered for that wind load. But normally you do have some clearance around an array from the edge of a roof, and it's also for access reasons. You don't want to be having to move a ladder all the way around your roof to kind of clean the panels. Also, if you're on a residential installation, it makes it dangerous for people to walk around the roof if they're right on the edge. So those are some of those considerations. I'm just going to jump forward a little bit, and there we go. So that's the north face of a house. Now, a little bit of non-solar talk here, or non-solar electric, is passive solar design. I often say the biggest savings in terms of cost of energy is good design of the building itself. It starts with orientation, insulation, thermal mass. Get those things right, and what's left over is a little bit of energy input to maintain thermal comfort. So having, this is all double glazed windows, north facing, a lot of thermal mass, concrete slab. There's a large thermal wall inside the building as well. And all that kind of really helps moderate temperature. We burn wood for heating predominantly, and that's hydronically circulated through a concrete slab in the floor. And just scrolling over a little bit, gardens, and there's that tiny house. So just showing you how close the little tiny house, that's a neighbour's house. Here on the co-op, by the way, we don't have fences because we're all on one property. It's all collectively owned. So we basically just have paddocks with houses dotting around the place. Now, going to go back to some of those questions. Let's have a look here. Yeah, Craig says it gets chilly. And I've got a Solar Plus question. All right. Okay. Let me bring this one up on here. So for those who don't know, I actually part owner of another business called Solar Plus. We started it 10 years ago, me and Laurie Kane, and we produced solar design software, which has matured tremendously over those 10 years. So it's designed for on and off grid systems with generators, with solar, with batteries. So it's a full package design tool, but it's really aimed as a commercial tool. So it's not a free tool. You subscribe to it. So it's for businesses who want to streamline their design and installation processes. Yes, indeed, Sadesh, Solar Plus does calculate payback periods because it does a full system analysis in terms of production based on both your load energy. If you've got any data, it can take data from smart meters, for instance, and do a full analysis of your load profile. Based on the amount of PV, the orientation, inclination, your zone, your location, all of those factors, even down to D-rate for shading, and therefore can produce an economic analysis. But since we're talking off-grid here, Sadesh, I'm going to kind of pivot a little bit here and draw another picture. So one of the things to consider with off-grid is how much does it cost? And I've already had some comments with my promo for this show that it's easy to design a system for off-grid. You just ask them what their budget is, and that's what they get. Well, let's kind of approach that a bit differently. So I'm just going to bring up my little drawing pad again. So I'm going to cut over to that, and there it is. So I say there's often three ways to size a system for off-grid. So sizing a solar PV plus battery system for off-grid. Now, step one, and I'd say this is an order of best to worst. Step one is finding out what the customer's loads are. So I call it to a daily load requirement. So how much energy do they need per day? Now, that can often be a very difficult process for a new build where there's no home to start with. But you want to find out what their energy requirements are. That's when a load sheet comes in. Customer will fill out a load sheet, identify the appliances they plan to put in their home, how many hours they're going to run them for, sometimes duty cycles for things like aircon and fridges, and work out how much energy they need per day. And then build a system to deliver that amount of energy. Step two is a fixed size. That means you say, e.g., this is our 10 kilowatt hour per day system. That means, for a particular design month, hopefully the worst one, like wintertime, it will produce 10 kilowatt hours per day of energy. And, there's a cost associated with this. So, there's the cost of that one. This one, you're leaving the choice to some extent up to the customer. They'll go, yeah, I reckon 10 kilowatt hours a day will do me. I'll go for that system. It sounds cheaper. And then number three is to a budget. So they just basically tell you what they want to spend. And of course, everyone likes to spend as little as possible. So sometimes you start with one and you end up with three. But really, if you're a salesperson, you don't just take, I'm going to cut back to myself. Here we go. You don't just take someone's estimate of what something's going to cost and then build it to that. You try to explain to them what the implications of that are. And, from my experience, having designed systems for many years and installed them, you get customers who have totally unrealistic expectations. So it's expectation management as well. They might just assume that they can live a normal life with all the appliances they currently have for a very small amount of money. Unfortunately, on-grid solar's got incredibly cheap, and so people assume that off-grid is incredibly cheap too. But the big difference is energy storage, and scale. You don't need, you need way more than 1 day's worth of storage for a start, because you get bad weather and you want it to run for a longer period of time before you have to bring in a backup generator. So there's a much bigger cost associated with meeting a larger energy demand. Now, how do you solve this one without going through all these steps? Like step one, go through all this process of coming up with a load sheet, getting it filled out, calculating the size system, costing it, giving it to the customer, and they go, oh, I thought it was only going to cost me 10 grand, and you're telling me it's going to cost 60. You're dreaming. Well, there's a kind of shortcut to this, which is have some ballpark figures straight out of the box that you can give them that actually helps them understand the cost of energy. And my favorite one is talk about dollars per kilowatt hour of system build price. Now, this is not the price you would buy electricity at. This is the price it costs to build a system to deliver a certain number of kilowatt hours. Now, I use a couple of figures. If I cut back to here, I often say, at the moment, something like $2,000 to $4,000 per kilowatt hour per day is the build price of a system. Now, you might think, whoa, that's a lot of money. If I use 10 kilowatt hours per day, does that mean it's going to cost me between $20,000 and $40,000? Yes. That's for a well-designed system to actually reliably deliver that amount of energy. Now, why is there such a big range in here? Is that just your profit margin? Actually, that reflects the amount of storage you have. How many days of autonomy? How many days can you go without just running off renewable energy before you have to start a generator, for instance? So that would be more like 5 days. This would be more like 2 days. So you've got a bit of range there in terms of quality. But these prices all based on your equipment and selection. So something, if you're an installer, you would do the costings yourself. It therefore clearly indicates to the customer, bring myself back on, that it's all about, I keep disappearing. It's all about energy. So every kilowatt hour that they use is costing them another $2,000 to $4,000 in system build price. So the problem isn't the cost of the system. The problem is their energy demand. Get that down, you save lots of money. Now, that's where the conversation goes quickly towards energy efficiency. You can save huge amounts with more energy efficient appliances rather than hanging on to those old clunkers that you've had for decades, particularly things like inefficient fridges. You might have a 20-year-old fridge and a spare one that's been out in the shed, and you want to take those off grid with you. They're going to cost you a fortune to run because their star rating is probably 1 star. So those are some of the considerations when it comes to costing. Okay, back to questions. We've got a whole mixture here. Can we have some technical installing questions, please? All right, straight away, Rob responds. Thanks, Rob. So, g'day, Rob. Nice to see you there. Rob says, now he's referring to the new battery standard ASNZS 5139, and it refers to, and boy, that's a long clause number, isn't it? 6.3.1.3.7. You've got to say that, many times to get it memorized, that there is a 2-meter rule for the length of cable from the output terminals of the battery system to its point of isolation. So that's cable run, not just physical distance. Basically, you're trying to reduce as much as possible both overcurrent protection and isolation of cable that's not isolated or overcurrent protected. So that 2-meter rule means more or less you want it as close as practicable. Are we sure it shouldn't be actual distance? No, it is actually, it says cable length in the clause from memory. So unless you've got it there, I'm not going to look it up, but I'm pretty sure it's cable length. Many battery systems, by the way, have inbuilt isolation. So in a way, it's 0 meters because the product itself has an inbuilt isolator. So that's always a big plus. Now, time for me to bring up another little tour. So let's have a look here. I'm going to start going into the lab now. So this is, I've got, I think, six kind of labs now, or rooms. Some of them are separate buildings. Some of them are just partitioned within a larger building where a lot of equipment's installed that I use for testing and training. And so I'm just going to hide that one, Rob. And sharing the screen again. Here it is. All right. So this is There we go. Sorry for the grainy picture. It's not very bright when I filmed this morning. So the system you're looking at here is a couple of Inga team inverters. These red ones on the wall here. There's a lot of inverters in this room, but we'll just focus on a few at a time. Those are Inga team inverters. It's a Spanish company, by the way. They're 6 kilowatt hybrid inverters, but they're actually designed as an off-grid inverter primarily that can take PV as an input, can take a battery, and can take an AC source like a generator or the grid, and as an AC output, a dedicated AC output. So it's got all the kind of, bells and whistles that you would need, and it's all in one box. That's kind of a nice thing. So it can be used on grid or off grid. What we've actually done here is got 2 different battery systems. We've been doing some sort of R&D work with Pylon Tech and Inga team, integrating different systems together. We've got on the left-hand side the Pylon Tech Force H1, which is their kind of stackable modules. So you can have I can't remember how many you can go up to, but more than 3. So we've got 3 modules there. And each time you increase another battery in the stack, your voltage goes up. Now, that's one of the advantages of the Inga team is it's a high voltage battery input inverter. It can take up to 300 volts on the battery port and as low as 40 volts. So really you want to be above 120 to get full power out of these inverters. So let's say 120 to 300 volts is kind of where it's at for the battery port. Next to it on the right-hand side is a cabinet. Now, I think I've actually zoomed in on this, so let me just take you a bit closer. That's just the screen on the front of the Inga team. There we go, showing just the basic information that customers need to know. How much is in the tank, the battery, how much is coming in from the solar, how much is going out to the house, and how much is coming in from the grid or a generator. And down below it, if I scroll down a bit faster here, there we go. There is the Force H1 with my laptop bag on top. And you can see it's got 1, 2, 3 battery modules stacked on top of each other. That's become a very popular configuration for batteries I've noticed lately, is stackable batteries. That means a small footprint and you can increase the capacity by just stacking more on top of each other. So great for space. But next to it is the rack mount solution. So opening up here, these are 19-inch rack mount style battery modules in a vertical orientation. And so you can have up to, I think, 6 in that cabinet. We've got 5 battery modules plus the BMS controller. We've got 4. Each one is 50 volts and they connect together in series. So that's a 200 volt battery pack. And that's feeding one of those 2 Inga team inverters. Incidentally, the purpose for these 2 inverters at the moment is to provide a dedicated electric vehicle charging point. They're set up so that they'll only discharge their batteries into the electric vehicle socket outlet, and once the battery is empty, turn off that socket outlet. So it's just a way of dumping surplus solar at nighttime into an electric vehicle. Moving on a bit. Oh, gee, that's slow-mo. Hang on. Moving on a lot faster. Sorry. Here we go. And next to it is a Australian icon, the Cellectronic SP Pro. Excuse the open switchboard. My electrician was doing some work on the system when I took these pictures. The SP Pro, Cellectronic SP Pro, this company's been around for over 55 years. It's based in Melbourne. They make probably one of the best off-grid inverters in the world. I've even heard their competition describe it as such. It comes in a range of sizes from, I think, 3.5 kilowatts up to 20 single phase. And you can do multiples, multi-phase with multiples of them, and you can do multiples per phase. So I've got a power chain here with 2 inverters per phase, 3 phase, that's 6 inverters. Makes for quite a big setup. Connected to it is now a now discontinued LG Chem, the 13 kilowatt hour unit. They've brought out a new model now, but that's just sitting there below it. I think I've scrolled back a bit, you'll see it a bit better. There you go. So that's a lithium ion battery. One of the shortcomings, though, of this kind of arrangement is it is actually limited to 5 kilowatts of continuous power, that battery. It will do 7 kilowatts for about 3 seconds, so it's got a little bit of surge, but you need to be very careful in designing a system that you don't exceed that, otherwise the system will shut down. It won't damage the battery. They're very good at protecting themselves, but it will just the inverter will shut down. So there you go. That's a it can be an off-grid system, or that could be an on-grid system. Either is possible. All right, so looking at the questions here. Here's a a popular one. What are the pros and cons of lithium versus lead acid gels? That's probably a whole Toolbox Tech Talk in itself. So probably some summary things is, I think we're in a transition period globally for batteries, which is lead acid is a 150-year-old technology. It works. It's worked well for 150 years. It still works well. There is still a huge amount of lead acid batteries being sold and distributed, and almost every vehicle has one under the bonnet. So it's a very common product. It's I've been told that it's the most recycled product by weight on the planet, because lead is valuable. Even at end of life, a lead acid battery still has value. That means it's not going into the waste stream, so it's generally being turned back into another battery. So that's a great thing. But it has its shortcomings, and some of those are cycle life, short cycle life compared to modern technologies like lithium. Maximum depth of discharge is much more restrictive. So typically, 50% or more, maybe 60% maximum depth of discharge to get a healthy life out of a well-designed lead acid battery. So you have to have that reserve capacity that you try not to ever use. They're heavy. They're generally designed certainly for off-grid as 2-volt cells that you connect in series, and they can't be upgraded. So if you've built a system out of 2-volt cells, let's say it's a 48-volt system with 24 cells in series. 5 years later, you want more capacity. You can't just add another string or another battery, because you can't mix old and new. It's bad for both. Whereas lithium solves those problems. Lithium and other chemistries, which are modular, basically you can parallel multiple batteries together to achieve the capacity you require, and you can upgrade them within reason later down the track. So, there's some straight up pros and cons. For me, just the weight factor is a big one. Many of the modular lithium batteries that are rack mounted are only like 30 kilos or so, though some of the floor mounted ones, like the one in the picture here, that's about 100 kilos. But they, can be moved on trolleys quite easily. You don't have to lift them up into racks, etc. Though wall mounting does bring in a bit of weight issues. So weight's one of those other considerations too when you're looking at batteries. All right, I think I've got a couple more walkabout images while here we go. So there's a new one. Sorry, it takes me a moment to share my screen each time I do this. So now this is a system from Sonnen. Now, bring it up here. There you go. So very grainy, because I didn't have the lights on, because I mentioned at the beginning of the show we actually had a blackout, so we lost power. So this is a Sonnen system. Sonnen, German company, 10 years of R&D have gone into producing this product, and it's actually made in Australia. So those little made in Australia stickers are for real. They're made in South Australia, even though it's a fully German designed product. And of course, components come from all around the world, but these are assembled in Australia, and the support is based here too. This is designed as an on-grid system. So today's talk about off-grid and batteries, I guess this would fall into the battery department. What sort of battery is this? It's a lithium ferrophosphate battery module. There's two 2.5 kilowatt hour battery modules inside that cabinet, but you can actually get an external cabinet and have up to, I think, about 15 kilowatt hours total with an extra battery cabinet that sits below the main unit. It's a hybrid inverter. That means it's got solar input, so it's got a dual MPPT. It'll take happily, I think, 6 or 6.5 kilowatts of PV. It's got a backup capability. Now, they've tried to make that as easy as possible by providing a separate product called Sonnen Protect Plus. That's the little box on the left there. And I think I've actually opened it up for you. They've simplified the process of wiring up one of these things. Gee, it's grainy. Sorry, that picture is pretty terrible. Just open it up here. And so they've pre-built a fully wired up enclosure with contactors behind those blanks, some contactors so it can do break before make switching for backup. It's got an energy meter. It's got an Ethernet port so you can be connected to the cloud. It's got circuits for AC coupled solar, grid, and the Sonnen battery. So all of that is pre-built. I didn't do anything there. We just stuck it on the wall and my electrician connected it up. So there you go. Now it's a bit grainy, so I'm going to move back a bit. And it's got all the signage. We didn't even put the signs on. They're already there. So this is kind of like trying to make life easy for you. One thing to note about Sonnen is unusually all their connections are at the top. I haven't seen this with any other product, but there you go. They're sort of out of kids' way. So no one's going to be fiddling with your system because these are designed to be about 1.8 meters up the wall. So all of those connections are up the top there. Now, straight away, you can see that this is an indoor-only product. So you won't be putting this out in the rain because it will just get straight in there. So that's an indoor-only product. How do you like my fake brick wall, by the way? It's one of those photographic backdrops. It used to be nice and black, but it seems to have faded in the sun, gone sort of magenta. All right, coming back to questions. Yes, Heath installed his share of Sonnen. Well, boy, they're heavy. 2600s. So, yep, that's probably about a 100 kilo battery, I'm guessing. That's a backbreaker for sure. And another comment about lithium here from Brendan. Self-built high-capacity lithium batteries seem to be gaining popularity. Self-built as in DIY. Yeah, it's not something I really go for myself for anything other than just a home project. You don't want to be self-building and selling them. But, you know, if you're a DIYer and like to make your own projects and you know how to do it safely, just be aware that lithium batteries can get into runaway conditions if you don't manage the charge very carefully. So they do require a fair bit of safety when working with them. And this is Ray's a great font of information. So hi, Ray. Great to see you again. Did you hear that 80% of Tesla battery materials are sourced from Australia? So no surprise that Sonnen is made in Australia. I guess you're referring to the lithium, I don't know, or the metals. I'd like to know how they got that 80% figure. But yeah, Australia does have lithium mines. So as we do with iron ore, it gets shipped overseas and turned into a higher grade product, and then we buy that back again. Oh, thanks, Bradley. I thought the graininess was worse than that. All right, so let me just drop out now. I've got 2 more to go, and we're at 3 o'clock. I normally try to finish around 3, but you guys are so engaged. I'm going to go the whole shebang here and show you 2 more videos. Now we're getting more into the larger systems here at the lab, and this one is a Solar X. So Solar X have been in Australia for quite some time. I've had a range of their inverters, Gen 1, Gen 2, and this is their Gen 3. They really are an on-grid hybrid battery. So I guess I'm branching away from the off-grid theme here. The reason I say that they're really an on-grid product is products designed for off-grid often have a couple of extra criteria that, in my mind, to make them suitable. One is that they have the ability to auto-start a generator. So they need some form of voltage-free contacts that can be used to with a 2-wire start to an auto-start generator, turn it on when required. So reliable power irrespective of solar and battery state. But most hybrid inverters don't need that and don't have it. The other one is overload capacity. When you're off-grid, you don't have the grid to help you. So as soon as you turn on an appliance and it surges, it will draw an inrush current depending on the nature of the product. That surge can be 2, 3, 4 times what its run power is, and the inverter actually has to deliver that. So an off-grid, you need a lot more surge capacity, and that generally means a large transformer-based inverter. They're heavy. So the Cellectronic SP Pro that you saw just before, that's a heavy inverter because of the size of the transformer, but it has, a 2.5 times surge factor. So it can deliver 2.5 times its continuous rated power for like 30 seconds. So it can really, turn those big motors when required. So I'm just going to play this one. We'll move in a little bit here. So what you're looking at is two separate SolarX systems. The big tall one is the 3-phase 10 kilowatt, and the one on the right of it is a single-phase 6 kilowatt. And each of them have a string of batteries. I'll just pause that there. Please pause. These battery modules, they're called triple power. I've actually been to the factory in China where they made these. Pretty impressive, fully automated factory. It's just amazing how fast China builds, factories to deliver product, but also the level of automation going into these factories. These batteries are made in a factory where there's minerals in one end, through a whole robot 1 kilometer long production line, mostly all robots, and then batteries come out the other end. Amazing. So these batteries are 100 volts each, and they're connected in series to get the appropriate voltage for the inverters. The 3-phase inverter goes between 3 and 400 volts, so either 3 or 4 battery modules, and the single-phase inverter, either 2 or 3 battery modules, so 200 to 300 volts on the battery side. Now, you might think, gee, that's pretty high voltage battery. There's a lot of pluses now with high voltage batteries, which is small cables, longer cable runs, mechanical protection is easier, your cost of your isolators and overcurrent protection devices is much lower. You're not switching hundreds of amps, you're switching tens of amps. So this 10 kilowatt inverter only draws like 25 amps. It makes very easy to wire them up. It's a bit like just a solar system, really, but it's a battery in terms of cabling. So there you go. And on the left-hand side of the 10 kilowatt SolarX, there is a contactor inside that enclosure. It's an add-on product. That's so it can switch into backup mode using a contactor, so it will be able to run independently of the grid in 3-phase. This also has a feature which is not that common, which is called unbalanced load support. So when you've got solar and batteries connected and you're on grid, you don't have to produce the same amount of export on all 3 phases. So it can actually support one phase at a different rate to the other 2 phases. Now, this is probably no big deal for Australians, but for New Zealanders, where you get billed per phase, which is kind of unusual, I think Slovenia and New Zealand do it this way, this is a bit of a plus. So you actually can get the maximum financial benefit by self-using as much of your solar energy on the phases that need it without giving away on the other phases. So a quick little scroll around here. And that's just showing the display. The battery's virtually empty because of our power outage here because the generator failed. Don't worry, Bradley, your batteries are still working lovely. We've just got a bit of solar onto them directly. Some DC coupled solar, that is. Did I film this in slow-mo? Hang on, let me just speed this up a bit. And on this side of the room is a completely different system. Now, I'd say this is more likely to be an off-grid system than the previous example because it's a Victron Multi-Plus 2. Now, they can be used on-grid as well because they are 4777 compliant, but they are have all the features that I just listed before in terms of having a ability to auto-start a generator, having a good surge capability, and they can work in single or multi-phase. So what you're looking at here is 3 5 kilowatt multi-plus 2s, 1 per phase, and they have a synchronization cable that goes between them so that the master or the on the left controls the phase angle of the other 2 and therefore creates true 3-phase. Below it in those lovely silver boxes is a couple of red flow batteries. Now, I didn't want to take the covers off because it was just too much work and it's freezing cold at the moment, and they actually like to be kept warm. So we're at 5 degrees here. These batteries work best above 15 degrees Celsius internally, so we do kind of keep them a little a little toastier with these wraps. But normally they come with an outdoor enclosure, which we didn't have. We just had the bare battery module. So the outdoor enclosure would provide some of that protection. Ray just asked, since I've got this up on the screen, Ray asks, why not Quattros? Well, that's what Victron gave me. So Quattros are their dedicated off-grid inverters, whereas the multi-pluses can be used on-grid and off-grid. So, just a bit of flexibility, I suppose. We've also got them being controlled by another device called a servo. So I'll just zoom in on that for you. Servos are a smart controller. Let's see if I can zoom into it. There's the screen of the it's the screen from the servo showing you what's happening. I'll just press play so you can watch the little dots move around. As you can see, the grid's off at the moment. The red box is the microgrid because, as I said, we've got a little bit of a power outage here. And down below it, if I scroll down, is the Servo GX. Now, Victron have a whole range of GX devices that they've brought out over the years, and basically they're kind of the smarts that connect all of their products together. So MPPTs, inverters, shunts, all sorts of things can connect into it. It's got an Ethernet port, so it connects to the cloud. It's got digital inputs, digital outputs. It's pretty amazing what this little box can do. That's the blue box in the middle there. On the left, though, is the BMS for the Redflow battery. So it has its own battery management system. And on the right is a switched-in droplet, which is used for monitoring of the system as well. So quite a complicated little setup there. Now, I better get on to the key part of today, actually, which is sizing an off-grid system. Now, we talked very simply, about pricing one, but now we're going to look at the equations for sizing one. So, I'm just going to stop sharing that. And sorry, there's so many questions come in. I think I've skipped over a few. Just scrolling back through them now. Here's just a general question or comment. What do you think about AC protection? I came across an off-grid system where the fault loop impedance of the inverters was 2.5 ohms, and therefore more impedance than table 8.1 allows to provide. Now, this is an interesting one. Fault loop impedance is what you rely on to trip your overcurrent protection devices so that you can remove a fault. So let's say your oven has a loose wire in it and the active touches the frame of the oven, and the oven's frame is earthed, you really, really want that not to be live. And you want your circuit breaker to trip and to turn off that circuit, and therefore there's no shock hazard. Also, there's no potential for fire and arcing. But if you have a limited capacity, now the grid is kind of like an infinite capacity, given that you've got very low fault loop impedance and very large capacity, typically 60 amps or more on a single phase home, you can get a very large inrush that will trip virtually any protection within your home. Well, should by design do that. But when you've got an inverter, let's say you've got a very small inverter, you've got a 2 kilowatt inverter, it can only deliver 2 kilowatts, but you've put a 32 amp circuit breaker on the output of that, it's never going to trip. So you actually need to size the protection to suit the maximum amount of inrush that can be provided by the inverter. So, the fault loop impedance, it's a bit of an interesting one for off-grid. Thanks for that one, Mike. And just covering off from one last question before I go over to my design calculations. Hi, Glenn. When connecting a generator to a solar system, does the solar have to be connected on the utility side of the generator changeover switch? Okay, so this actually relates to AS/NZS 3010, which is the generator standard, which was updated a few years back. And it says that it's kind of got two steps to it. You can't have a solar inverter on the load side of the generator. That means the generator is supplying the inverter and vice versa, unless, and this is the second part of the equation, there is a control system to protect backfeed. So most inverters which have a generator input and maybe AC coupled on the load side to a solar inverter, manage that backfeed. Also, many generators have a backfeed protection circuit as well, so that they can't be reverse powered. Unfortunately, it's a bit of a dad joke. You can't reverse power from a solar inverter into a generator and make diesel. It's a one-way device. So you've got to protect it from reverse power. So yeah, the question really comes down to whether there's reverse power protection or not, and whether you can connect the solar on the generator side of the load side of the generator. All right, so last up, and I might actually have time for one more walk and talk at the end, but we'll see how we go. Walk about video, which is just looking at the microgrid system here. But before I do that, I really wanted to bring up my design calculations. Now, for those who've done my off-grid course, this would be old hat, but here we go, my solar and battery course. But I like to call this my 6 easy steps to designing a standalone power system. What we're looking at here is a really dumbed down version of ASNZS 4509 Part 2. Now, if I kind of, this standard here, 4509 Part 2. It's last published in 2010, I think. We'll do that. Part 1 was 2010. Part 2 was 2009, I think. Yeah, so it's about 11 years old, but that's actually not too bad. Not a lot has changed. Maybe AC coupling is probably not well addressed, but this is the design process. Now, there's actually 16 pages of formula in the back in Appendix A of 4509 Part 2 to design a system. I used to teach that, and it just seemed a bit over the top for what most people needed. So I kind of just dumbed it down, which is understanding the key ingredients to sizing a system. So let's do this in like 5 minutes. Of course, you can always go back and review this slide, because when this live stream finishes, it's still viewable and you can scroll back to it. So what we're looking at here is A is where it all starts. You need to know what you're trying to design a system for. So what their load energy requirement is. And remember, I said that it's often important to give the customer an idea of cost. You can explain to them, it's going to cost them $2,000 to $4,000 per kilowatt hour to build a system. That number there, the smaller you can make that, the cheaper the system will be. And the cost savings are very, very proportional, especially when you've got efficient appliance choices like a fridge. Battery system voltage, you need to know what that is because it helps with the mathematics, basically. So I'm using a nominal 52-volt lithium battery in this design. Section C, or step C, is I need to actually allow for the losses in the system. So you might need 9,000 watt-hours per day, or 9 kilowatt-hours per day, it's easy to say, but you are going to have more of that in storage because of losses. Some of those losses are due with round-trip efficiency of the battery, charging and discharging it. There'll be some energy loss in that process. Some of it's lost in the wiring. There's heat, thermal losses, and some of it's lost in the inverter, conversion from DC to AC. And those numbers there reflect typical factors for efficiency of a battery and wiring and inverter. And so overall, if you are referring to that as percentage, that your load subsystem efficiency is around about 83%. Now, you can put your own numbers in here to suit the products that you choose. Step D, gee, look, we're past halfway already. Amp hour demand is really just how many amp hours per day will you demand from your battery system. So that's just A divided by B divided by C. A divided by B, blah, 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 gives me, in this case, a worked example of 209 amp hours per day is what I'm going to be taking out of my battery system to deliver 9 kilowatt hours per day of energy to the customer's loads. The hardest one actually is step E, and I'm kind of going to keep it a bit simple because a lot of this is dependent on where you are and what the solar resource is. So yeah, it is a little bit particular, but I'm just going to move it up a bit so you can see it a bit better. So sizing the PV system, you got to know what the energy demand is. That's A. You got to know what your solar resource energy per square meter is, and that's your peak sun hours. That's something that you could look up in tables or software. You need to know what the system efficiency of your whole PV system is, not just your panels, but also your inverter, your cables, your dust and dirt derating. So that's, in brackets, there are all of those major factors. Thermal losses, i.e. as panels heat up, they lose power. Wiring losses, inverter losses, and dust and dirt. There's even other ones, but those are the main ones. And then you are going to divide it by the subsystem, load subsystem efficiency factor as well. And that's sizing my PV for this design with a peak sun hours in winter of 2.7 peak sun hours, which is basically here in Melbourne, north facing in Melbourne at about 50 degrees tilt will give me 2.7 peak sun hours. I need 4.7 kilowatts of panels. It's not too bad, actually, 4.7 kilowatts of panels. But that would be unshaded, north facing at a 50-degree tilt. So you can see this number here can easily be increased to, to suit a little bit of overcapacity for those poor days, but it's often the cheapest way of reducing the cost of your battery storage, because I'll get onto that last. And battery system sizing really is all about how many days of no input from renewable sources, what we call days of autonomy, just running off your battery. Now, in 4509 Part 2, it's assumed that a day of autonomy is a total eclipse, absolutely no input, but we know there's always a bit. So it's really a worst case scenario. So how many days of total eclipse can your system run for? The recommendation in 4509 Part 2 is if no auto start generator is available, 5 days of autonomy. If there is an auto start generator available, minimum of 2 days of autonomy. Now, those are not shells, they're just recommendations. So let's say somewhere between 2 and 5 days would be a good range to look at. I've chosen 3 here, and then I need to allow for the fact that all of my battery can't necessarily be used. So many batteries rate their capacity in total capacity, and then we'll say, but maximum depth of discharge is 80%. So in this case, 90% maximum depth of discharge. So I can use nearly all of my battery. I've got 209 amp hours per day demand times 3 days of autonomy divided by the maximum depth of discharge tells me that I need a battery system of 697 amp hours. Now, if you want to convert that to kilowatt hours, you just multiply it by your battery system voltage, which was 52. So I need 36 kilowatt hours of total battery capacity to be able to deliver 9 kilowatt hours per day for 3 days during a total eclipse. And where have I gone again? There I am. Okay. That was really quite rushed, but I just wanted to kind of make sure that you got the key formulas for sizing a standalone system. Now, those same formulas can be used on grid as well, but it would be for backup capability. So instead of days of autonomy, it would probably be more like hours of autonomy or a day. Instead of load energy requirement for the whole house, just for the backup circuits, they'll be the main differences. And if it's DC coupled storage, a DC coupled solar, the solar is going to keep you going for longer. But if it's just an AC coupled system that can't run without the grid, then it'll just be how much is in the battery, and then the lights go out. So there's a couple of considerations. Right. Going to just finish off with last little video and then a few more questions, and we'll close off. Wow, nearly an hour and a half. This is my longest session yet. Got to bring up that shared screen. Told you this is my favorite topic. I talk all day about off-grid and batteries and solar. So this is me just walking uphill from my house towards one of the labs. It's still like an open shed. A lot of these were just old carports and things which we converted. And this that I'm approaching is known as the Tower of Power. So it's not a brand name. It's just what we call it because it's such an awesome looking thing. This is Power Plus Energy's eco batteries, 48 volts or 52 to be exact, batteries in a 20 battery stack. Hence, it's a tower, like 2 meters tall, and each of those batteries is in parallel with every other one through a bus bar at the back. So there's a big couple of bus bars that all of the batteries parallel onto. Now, one of the nice things about these batteries is they have an inbuilt circuit breaker on the front of them, which is rated for load break. It can be locked in the off position. So it meets all the requirements of isolation. You don't actually have to have a single isolator for the whole system. You can actually isolate through multiple points as long as they're in the shutdown procedure. So, to shut down the system, the shutdown procedure lists turn off isolators 1 through to 20 on the, after you've turned off all the AC, of course, and the inverters on the battery module. There's also a little box up the top there, the power link, which is a kind of a bonus feature they've got here, so we can monitor it through the cloud. So they've got cloud monitoring options as well. And those little lights that are flashing are just showing the polling of the batteries. So each one is being polled by the PowerLink device, and that data is being collected and sent through to the cloud. Okay, now I'm going to flick over, and you can all say something nasty to me, which is, Glenn, you keep going on about HRC fuse switches, and then you've got 2 of them on the wall. Well, this system is about 5 years old, so actually it predates the change in 5139, where you're required to have IP23 isolation on your batteries, between your battery and your inverter or PCE. We are going to actually remove these just to make it a best practice example, but these aren't IP23, they're IP20. So no longer would we be able to use those. Now, I did say that I had a power chain system from Selectronic. This is 6 inverters, 2 per phase. Each of them is a 5 kilowatt inverter, so it's 30 kilowatts of 3-phase power, and they make for quite an impressive row. There they all are, going down the wall. Now, lastly, at the end of the wall, there's a little box I want to take you to. So I'm going to jump right down there real quick, past the main switchboard, and past the shutdown procedure, which you've got to have. And right down here, there it is. So that's a maximum power point tracking charge control. It's by an Australian company called AERL. Incidentally, they invented the maximum power point tracker. It's an Australian invention. In Queensland in 1984, Stuart Watkinson made the first maximum power point tracker. So there you go. He had the global patent, I believe, till 2006. So that's a company that's been around for a long time. They also make a Earth Guard device, which is on the bottom here, which is an earth leakage detection that fits onto the bottom of the MPPT, which is a requirement under the new battery standard for anything over 60 volts. So even though we probably don't need it on this system, we've got earth fault detection on the battery side as well as on the PV side. Why have I got this? I've got all these big inverters, which I've got, like I said, 100 kilowatts of solar connected to this, because as soon as these inverters shut down, as they did the other night due to low state of charge, all of the solar would be off as well. And even if the sun came out, nothing would happen. But this MPPT has 4.5 kilowatts, I think, or 4 kilowatts of PV connected to it. And it's a DC coupled way of charging the battery system. So it directly charges the batteries, brings the battery voltage back up to a level that the inverters will turn on again, and bingo, we're back in business. Once the inverters turn on, the battery inverters, then the solar inverters synchronize with them, and we're charging again at full power. So that's a really nice use of a small amount of DC coupling on a predominantly AC coupled system. And Brenton says Encore. Yeah, okay. Look at all those SP Pros. Yep. Right. So back to me. Now I'm going to finish off with just checking any questions that I missed out. And yes, Brendan, I will buy some extra pesky voltage regulators for my generator. Thank you for that comment. I kick myself because it's only a sort of $80 product, but it means the lights go out and they stay out till I get another one. And Ray asks, oops, sorry, I click on it. There we go. Ray asks, is wind generation, oh my gosh, I'm going to sneeze. Must be time to finish. Is wind generation, do you use the same as the PV size calculator? Wind is a whole other complex box of tricks to calculate. It's way more, it's much more a high level engineering and maths problem than sizing for solar. You've got intermittency, you've got things like the design, the power curve of the wind turbine, so at what speed it produces what power, what wind shadow factors you have, the direction of the wind, whole bunch of things come into play when you're trying to calculate the production. Often the simplest way is just put up one and find out. So it's an empirical approach. I think earlier on, someone was commenting, don't get me started on wind. Look, really, times have changed. We lead acid batteries, 150 years old. Wind, been around for a long time. In fact, wind was the beginning at Murumura. There was only wind turbines here. There was no solar. It was too expensive. But what has happened in the interim is solar has got so cheap, and wind is still relatively expensive, and its maintenance requirements kind of make it less attractive. And certainly from an economic point of view, unless you have an excellent wind resource, it's way, way more expensive than solar. But it works at nighttime. So it's got its kind of special secret weapon, which it can work at nighttime. So if you're off grid and you have solar and wind, it gives you a little bit of coverage through the nighttime as well. So there you go. That's kind of like wind turbines in a nutshell. And Bradley asks, you shouldn't have asked this, Bradley. How is the single blade turbine going? Bradley knows we've got a few different interesting systems here. We've had a Darius rotor, which is like 40 years old now. It's huge. It's like 15 meters tall. Looks like a giant egg beater upside down. It hasn't worked for 39 of those years. But we have a single blade turbine from New Zealand. And unfortunately, it had a mechanical fault shortly after being installed. And 2 years later, we're still waiting for a part to repair it. So pretty much the story of wind. Maintenance is really important, and mechanical breakdowns can be pretty dramatic, certainly when blades come loose. So we've got, I think the only wind turbine working here at the Smart Energy Lab is an AirX, a 200-watt AirX that I've had on the side of my shed for about 10 years. It just works. I think of it as a weather vane. It tells me which way the wind's blowing and makes a bit of a buzz, so a little bit of noise, so I know how strong the wind is. So there you go. I call them wind ornaments. Look, I'm going to have to wind it up now. You have been the most awesome audience I've had in a long time. So thank you so much for turning up today for Toolbox Tech Talk. I had much more I wanted to cover today, but there was just so many questions. So look, apologies, I didn't get deeper into batteries than I was planning to. I think I've got to do another one of these Toolbox Tech Talks on off-grid solar design and batteries and try and dive straight into the tech a bit more. But, I like the fact that you asked the questions and I'm here to answer them. So anyway, hope to see you next Sunday, 2:00 for another Toolbox Tech Talk. Let's roll the credits.